During the making of this video, I lost a lot of my project data due to this bug in the program I was using. It prevented me from accessing the file to the project, so I couldn't edit it, I couldn't add anything to it, take away from it, I couldn't even view it. This is water. So I'll be talking to you about the Doppler Effect, which is something really cool that has to do with sound. I hope you enjoy. Hey, whatever, I'll just skip to the point. I'll be talking about sound, and you're going to listen to it whether you like it or not, so tough news. Man, he already started the video and it already sucks. Here on Earth, sound occurs when something hits air molecules, and they hit each other up to the point where they reach your ears and you're able to hear a sound. This is cool, because when you talk, you get something like this.
If I had $1 for every brain you don't have, I'd have $1.
Fun fact. Since there's absolutely nothing in space, you can't make a single sound in space, no matter how many times you try to ring that bell. Fun fact. You look worse on camera than you do through a mirror. This isn't fun.
As a source of sound moves towards you, the pitch of the sound you hear increases, and as the source moves away, the pitch decreases. It's called the Doppler Effect.
The equation for the Doppler effect looks like this. F equals C plus VR over C plus VS times F initial, where F's are the frequencies, V's are the speeds, and C is the speed of sound, which is, hold on a moment, 346 meters per second. F initial is the frequency of the actual sound, while F is the frequency of the sound that's heard by the receiver. VS is the speed of the source, and VR is the speed of the receiver. If the source of the sound is moving away from the receiver, then VS is going to be positive. But if the source is moving towards the receiver, then VS is going to be negative. VR is very similar. However, if the receiver is moving away from the source, then VR is going to be negative. But if the receiver is moving towards the source, then VR is going to be positive. For simplicity, we're going to keep the original frequency without a value, but the frequency can be any number as long as it's positive. To also keep things simple, we're going to have the receiver not move. So we're going to keep his speed at 0. You good, buddy? Alright, thanks. Since jets are able to go fast, we're going to use one. Jets can go at many speeds, but let's just say that this one is going at half the speed of sound towards the receiver, also known as 173 meters per second. Plug in all the rest of the numbers into the equation, then plug in the velocity of the source. It's negative because it's moving towards the receiver. Add them all in, and you get 346 meters per second over 173. Here you can simplify the number to get the frequency of twice the original. Now, as the jet moves past the receiver of the sound, then things change a little. For example, this changes to positive because it's moving away from the receiver. After that, you get a total of 346 over 519, which simplify that and you get 0.6 repeating of the original. Now get this, something interesting happens when it reaches the speed of sound. As it goes towards the receiver, get this, look at the denominator. Do you know what this means? It means you have to divide by 0, which makes infinity. It simply means you won't hear the plane until it hits you. But assuming you'd be absolutely fine, you get this equation, and you get 346 over 692, or 0.5 of the original frequency. What if it's moving faster than the speed of sound? Long story short, as long as you don't get hit, sound will be delayed. Here's what I mean by all that. As long as the source is going slower than the speed of sound, then sound will hit you faster than the source will. When the source is moving faster than the speed of sound, then the opposite occurs. The jet, for example, will fly past you before you get to hear it, unless it flies directly at you, but we're not going to show that again. Let's just say this jet is moving at faster than speed, 400 meters per second. Whatever, you know what to do. Have it be negative, and you get 346 over negative 54, which sums up to negative 6.407 repeating. I have way too much time. There's just one catch. That equation is only used when the source of the sound is heading directly towards the receiver. Usually, the sources of sounds are not moving directly towards the receiver, since there are plenty of other directions to go. Well, then how do you find the frequency then? All you have to do is use an angle, as long as the source is moving in a straight line. So you could take the angle of its straight line and the position of it compared to you, and use it in the equation like this, because the source is moving at an angle compared to the receiver. That being said, there are plenty of possibilities of angles depending on the distance it is from you. The further the distance, the smaller the angle. Now if the angle is 0, like before, the source is heading directly towards you, and cosine of 0 degrees is 1. Therefore, Vs times 1 is 1. Now assume you were right here, and the source of the sound is right there. If it's heading towards you, then its angle would be 0. But if it was heading perpendicular to it, it would be 90. When its angle is 90 degrees, the source is neither moving towards nor away from you. So cosine of 90 degrees is 0, and Vs times 0 is 0. Therefore, you're left with this equation, and as long as the receiver of the sound's speed is 0, then we can simplify the equation to have the frequency heard be the actual frequency made. And that's the Doppler effect, and the end of my video. Luckily, there wasn't much to define other than the Doppler effect, but I hope you found everything understandable, and I wish you a good day.